up to this point we have seen the one single axis operation, that is the two-fold axis operation. We looked at the two-fold, the mirror, which is also two-bar operation, and then 2 by m, which is the center symmetry involved operation. The same logic can be applied to the single rotation involved space groups. For example, if you go to a tetragonal space group, and if there is only one axis, which is the four-fold axis, the same logic of generating equivalent points and the asymmetric unit and the diagram which comes up with equivalent point positions being marked and the symmetry positions being marked can be generated. If you go to a hexagonal system or a trigonal system, again with single axis operation, those particular space groups can be generated in this way. In all the cases, the unique axis in those cases will be along the z axis, z direction. We have already seen that because A is equal to B in most of these cases, in all these cases. Therefore, we take the axis along the z direction and make the gamma angle 120 degrees in case of hexagonal and trigonal systems, and in the case of the tetragonal system, of course, it is still 90 degrees. So, what happens if there is more than one axis which now intersects at a point? So, there are several possibilities. The first possibility is the question of two-fold axis intersecting at one point. And when two-fold axis intersect at one point, we have been discussing this very many times, but I can just remind you that if there is a point here and then there is an axis which goes like that, a two-fold axis, and then there is an axis which goes like that, that is another two-fold axis, and invariably a third two-fold axis will be generated, and that is Euler's theorem. So, a point at this position, let us say P, a point P goes to a point Q and then goes to a point R, and then it defines a point group symmetry 2 to 2 because we can come back from one onto the other. So, this is the intersection of three two-fold axes. So, it generates point groups 2 to 2, and therefore, the space groups could be P 2 to 2, any of this A, B or C face centered, because now it represents an orthorhombic system, because the intersecting three two-fold axes will ensure alpha, beta, gamma is 90 degrees with respect to each other. A, B and C need not have any fixed values. So, we define now the orthorhombic system with respect to the 2 to 2 symmetry. So, the 2 to 2 symmetry will automatically now involve 2 mm, 2 by m, 2 by m, 2 by m. We have been discussing this over several classes. So, we are all familiar with that. Now, suppose we take a situation where instead of two-fold axis intersecting at a point like here, we have a intersection of two unscrew axis. So, now this becomes a two unscrew axis, this part we will remove, and let me remove that and show that. So, a two-fold axis, then there is another two-fold axis, this also becomes a two-fold axis. Then can three two-fold axes intersect at a point? This is the question. Neumann's theorem tells us that it is yes, two unscrew axes can definitely intersect at a point, and that is what is illustrated in this diagram. So, you have therefore a system, there are two intersecting sets of screw axes, that is what is given here. So, we take two intersecting set of screw axes parallel to A and B. What they produce is, for example, this is the A direction. So, we have a screw axis 2 unscrew here and a 2 unscrew there, a 2 unscrew here. Now, this intersects at the origin, this is our origin. So, it intersects the other 2 unscrew up there. So, when such a thing happens, we generate points. This point now will generate by the 2 unscrew operation that one, and then this one will generate this point, and by translational periodicity we bring it up here. And then we also generate from this point the 2 unscrew at 0.5, now we will turn around and bring this point. So, therefore, we have now systems in which we can have equivalent points as given here, where the two 2-1 axes are intersecting with respect to each other. What will happen to the third direction? Obviously, when we have these 2 points intersecting each other at 0 0 0. Suppose we take this as 0 0 0, then we generate a two-fold axis because of the fact you remember that whenever we have a translational component involved, the corresponding axis should move by 1/4. So, as a consequence here the axis moves by 1/4 in one direction, 1/4 in the other direction. So, it goes to this particular position and that becomes a two-fold axis. So, what therefore results is a space group which is now P21212. We will examine this space group in more detail in a few minutes, but at this moment the take home lesson is that if we have two intersecting 2-1 screw axes, because of the fact that they intersect with each other and they have to obey the Neumann's theorem, the third axis which will now get generated will be, because of the translation involved in the two directions 2-1 2-1, the half translations, the third axis will develop at only 1/4 the position, 1/4 along x, 1/4 along y, thereby generating this two-fold symmetry. And you can see that the equivalent points are nicely related by two-fold symmetry. And that is how we get to this space group P21212. So, we therefore have point groups, the space groups P222 and P212. Now, is there a possibility to have three intersecting 2-1 screw axes? And if so, what will be the validity of Neumann's theorem? Because the Neumann's theorem says that the intersection should be at a point. Now, obviously we see that if they intersect at one point, the third axis that is generated is only a two-fold. We can never generate a 2-1 axis in the third direction. But we do want a situation where we can have three intersecting 2-1 screw axis. Why not? Because if we are associating a two-fold symmetry with respect to a given direction, we have A not equal to B not equal to C, that is not a problem, but alpha, beta, gamma are 90 degrees. So, if you consider the parallelism with monoclinic symmetry, in a monoclinic symmetry, if you have y axis as the unique axis or the z axis as the unique axis, if you have two-fold symmetry, you will also have 2-1 symmetry. So, that therefore allows us to think that there must be possibility of having 2-1 2-1 2-1, 2-1 2-1 2-1 in each direction, which is allowed because each of the directions are quantified or qualified by a two-fold axis information. So, if you convert to the point group symmetry is still 2 2 2. So, since the point group symmetry is 2 2 2, it is an allowed symmetry. So, therefore, we should have 2-1 2-1 2-1 also as a possible space group, in which case how these get disposed with respect to each other. This diagram nicely illustrates that one comparing to this one. What you see here is that you will have two intersecting 2-1 screw axes, and now the intersections are not at 0.5 as you see here. The intersection is at 1/4 and 3/4. That means your first screw axis is going this way, the second screw axis is removed along the unit direction by 1/4. So, that means these two are not intersecting with each other, they are non-intersecting. So, if the two axes are non-intersecting, then this is not 0 0 0. Anyway, we do not need a 0 0 0 because this is a non-centrosymmetric space group. And so, we have one axis which is corresponding to 0.5 and the other axis corresponding to 1/4 and 3/4. So, if we have this kind of a system, one two-fold this way, one two-fold this way, removed by 1/4. Earlier they were coincident. The moment you coincide, the third axis becomes a two-fold. That is the space group 2 2 2 1 which we have shown here. So, in order to get 2-1 2-1 2-1, we have to move this by 1/4 3/4. Then what happens is, if you generate the equivalent points based on these two operations, you will get this point removed by half, because the two-fold screw axis is at 1/4 the distance from that whatever we call it as 0, and as a consequence we get half plus 0. Now, the relationship between these two clearly shows the presence of a 2-1 screw axis. Where is the 2-1 screw axis? This 2-1 screw axis is also removed by 1/4 and 1/4, 1/4 along this direction and 1/4 along this direction. So, this is a very interesting space group, very beautiful space group which can be generated, and the three 2-1 screw axes are non-intersecting and they are removed from each other by 1/4. So, if there is a direction A on which we have fixed the 2-1 screw axis, direction B will have a 1/4 removal, and direction C will be again removed by 1/4. So, 3 non-intersecting axes which occur at 1/4, 1/4, 1/4 from each other. So, this 1/4, 1/4, 1/4 is very significant because that will allow for flexible molecules to crystallize more comfortably, and that is how most of the organic compounds with asymmetric centers will crystallize in 2 1 2 1 2 1. It is a very commonly occurring space group. It is very interesting that symmetry now makes it very complicated in its arrangement, such that flexible molecules can also be organized into crystalline lattices. Otherwise, if these flexible molecules could not go into crystalline lattices, in principle we will not be able to crystallize. Now, what do we mean by crystallization in this context? By crystallization in this context is that we want to arrest the molecules obeying a certain rules of symmetry, and 2 2 2 is an allowed point group symmetry. So, therefore, the space group P 2 1 2 1 2 1 is also allowed. Once we allow the space group 2 1 2 1 2 1, the flexibility is associated with each of the axes. So, here is the very unique example where the 3 axes do not intersect at one point. They are removed by 1/4 with respect to each other. So, A direction is removed by 1/4 with respect to B direction, B is removed by 1/4 with respect to both A and B direction. So, we have therefore 3 non-intersecting screw axes displaced 1/4 with respect to each other. That is how we describe this particular space group. We will see the more details of it in terms of the space group diagrams now, and we see the first one, which is 2 1 2 1 2. You see now the space group number is 18. So, we have graduated ourselves from 1 to 18 now. Remember, there are totally 230. We are not going to obviously go through all of them, but here number 18 is now T 2 1 2 1 2 1 2 1 2 1 2. The point group symmetry is 2 2 2, and this is an orthorhombic system. And in the orthorhombic system, we have represented the two-fold symmetry. So, if you look at this diagram now, you know that this is an intersection of 2 two-fold axis systems, one along this direction and the other along that direction. So, this is a P21 axis, this is another P21 axis, and along the two P21 axes you see that the intersection point is shown at 0. In other words, the two-fold rotation is simpler operation than 2-1 operation, because the 2-1 operation has a half translation. So, when we have a space group like this, when we have realized that the intersection of 2 2-1 axes will generate a two-fold 1/4 away, then it is as well possible to push these 2 2-1 symmetries away from each other by 1/4 and put the two-fold at the origin, so that we get a definition of our origin. So, in this particular space group we get an origin, and at that origin we put the 2-1 screw in this direction 1/4 away and 2-1 screw in this direction 1/4 away. And this then generates this equivalent point diagram. You see that the asymmetric unit now will be x half and y half and z full, and you will see the relationship between these. This will be a two-fold rotation and this will be a two-fold rotation. You see that this is a two-fold rotation and you see that is a two-fold rotation, and so on. You notice that the 2-1 screw operation, which is 1/4 removed from here, will not generate any half positions here, because we are looking at the projection diagram down the two-fold axis. But what you see is the presence of the 2-1 screw axis here and the presence of the 2-1 screw axis up there. The presence of the 2-1 screw axis there generates what? Find out. I want you to study this diagram and see what 2-1 screw axis is generating which of these equivalent points. Of course, it will become obviously clear if you look at this list of equivalent points which are shown here. The Wyckoff tells us that there are 2 possible special positions in this space group, both of them corresponding to the two-fold axis along the z direction. So, since there are 3 directions, we put a dot dot 2 and a dot dot 2 to specify that the two-fold is along the z direction. It is not along either the x or the y direction, and therefore you have 0 half z, half 0 z bar, 0 0 z, half half z bar. Remember the similarity between this and what we saw when we took the z axis as the unique axis when we studied the space group P2. So, there is some similarity between the two. So, we get the special positions and 2 equivalent points in this and 4 equivalent points there. So, the 4 equivalent points generate x y z, x bar y bar z, that is the two-fold operation. You see the two-fold operation is restricted to the z direction, and then the 2 unscrew operation takes it to x bar plus half, y plus half and z bar, that is the 2 unscrew operation about the y, and the half adds up because the screw axis operation is verified with, is associated with the two-fold being associated with 0 0 0, otherwise we will not have had this equivalent. So, then we get this other equivalent point x plus half, y bar plus half, z bar. So, the molecules therefore, or the atoms or whatever the objects they arrange in this particular fashion, generating those 4 equivalent points. So, there are 4 equivalent points for P21212. So, P21212 is a very rare space group, but it occurs in many biological molecules. In fact, from the literature, if you go to the database and examine the database, you see many of the nucleic acid bases containing 1 unit of nucleic acid, that is something like what we call as a nucleoside. Many nucleosides, they go into this space group 21212. It is very interesting. You can study those structures and see why they are going into 21212. And that brings us the concept of the folding and the DNA folding and the axis about which the DNA goes through and so on. See, DNA has a helical axis, and the DNA components show 21212 symmetry if you take different blocks of DNA, and that is quite interesting. One has to study the database for this. Anyway, that is not the part of the course here. Of course, reflection conditions we will not consider now, and we go to 21212. Now, notice that in 21212 there is nothing at the origin, no symmetry. What I mean is there is an origin 0 0 0, but no symmetry element is associated with the origin. The symmetry elements are removed by 1/4 along this direction, and 1/4 along that direction, and 1/4 along that direction. So, these are the 3 2 screw axes. Again, the asymmetric unit is half along x, half along y and full along z, and what is very important is what is written here: origin at midpoint of 3 non-intersecting pairs of parallel to one axis. Now, this has to be examined carefully because we have 3 directions now. 3 directions are 90 degrees with respect to each other. So, every one of the 2 unscrew operations are happening parallel to each other and parallel to the 2 1 axis. But these 2 1 axes now are midpoint between 3 non-intersecting pairs. So, that means that if you take this origin, it is midpoint of 1/4, midpoint of 1/4, midpoint of 1/4. So, all 3 are removed by 1/4 from each other, and therefore, you get the origin here. And if you define the origin that way, then only you can generate this equivalent point diagram with the equivalent points coming at x, y, z as is given here. There is a certain amount of symmetry here in the generation of the equivalent points also. I will tell you what I mean by that. If you look at x, y, z, this it goes to x bar half plus y, z bar plus half, and then you see that this is now first the number 3 is x bar, okay. Number 2 is y bar, and number 3 is z bar. So, you have the 3 2 unscrew axis generating x bar, y bar, z bar, and since both the other 2 are removed by 1/4 and 1/4, you will have one of them positive, one of them negative. So, let me explain again. You have the x, y, z coordinate, okay, general position. Now, you operate one of the 2 1 symmetries, the 2 1 symmetry which will take you to x bar plus half, y bar, z plus half. Now, I want you to go back in this picture and identify where is that point. So, if you identify where is that equivalent point, then you will know what I am talking about. You see that there is an inherent symmetry in the generation of these 4 equivalent points, and I want you to identify that inherent symmetry. So, you go to each one of these equivalent points, find out how these equivalent points are now coming on the diagram which is shown before, because if you go to the international tables, all these will come together, except that this goes anyway into the next page the equivalent point information. So, take the equivalent point information and verify for yourself that we have these positions. Obviously, there will be no special positions in 2 1 2 1 2. That makes it very comfortable for organic or very flexible molecules to crystallize into 1 2 1 2. Now, one of the take home lessons could be, or for that matter an assignment could be, that the prove or show why there are no no special positions in 2 1 2 1 2. So, 2 1 2 1 2 1 therefore is very unique, and that has these equivalent positions, and there is only one Wyckoff position in 2 1 2 1 2 1. So, that way we have seen now a situation where we have looked at the more than one axis operation and we have taken 2 2 2. So, any one other than the more than one axis operation, which will give rise to tetragonal systems, it will give rise to hexagonal systems, and of course, obviously the isometric cubic systems. All these systems therefore have to be analyzed in this way. So, the presence of more than one axis of symmetry makes the equivalences related to each other in a much better fashion than just having one particular direction about which there is an axis like in monoclinic. So, the possibility of arranging more symmetric objects in higher symmetry space groups is very high compared to the probability of arranging more symmetric ones in the higher space group is more appropriate. So, it is very hard to find a coordination chemistry involved component in a 1 bar system or a 2-fold system. You will see them mostly tetragonal and higher. What I mean by coordination system involved is a very loose word. What I mean to say is that if there is a tetrahedral or an octahedral unit in a crystal structure, they prefer to go to those higher symmetry systems. Tetragonal and higher are the preferred systems for tetrahedral and octahedral geometry. Notice the difference. When I am talking about the geometry, I am talking about tetrahedral and octahedral, and when I am talking about the arrangement of the atoms, I am talking about octahedron and tetrahedron. And both these are possible, as we have seen from the point group analysis. In case of the cubic systems, we have the 4 3 2 and the 2 3, the two space groups, which will operate both on the tetrahedra as well as on the octahedra. Right. So, having come to this particular stage of P 2 1 2 1 2 1, we will now go to the MM2 system. And again, we will not take a simple MM2 system, we will take a case where we have also a translational periodicity associated with the point group, with the space group. The point group is MM2, the space group is PNA21. What does it mean? How do we describe this space group PNA21? PNA21 is a space group which is primitive, of course. P represents the primitive axis. N is a glide which is perpendicular to the A direction. N is a glide which is normal to the A direction. There are different textbooks which give different ways of interpreting it, but let us take these two definitions, which are correct definitions. N is normal to the A direction. Since we talked N as a glide plane, which is also a mirror effectively in the point group symmetry, the mirror has to be perpendicular to something, or it has to be normal to a given direction. So, there is a direction. That direction is characterized in this particular crystal system, which is the orthorhombic system in terms of a 2-fold symmetry, and M represents the 2-bar symmetry, and therefore, we have an N glide which is either referred to as normal to the A direction or perpendicular to the A direction. Similarly, we have an A glide which is perpendicular to the B direction or normal to the B direction. And we have the 2 1 axis. When we say 2 1 axis, we either say it is in the direction of the Z axis, or more appropriately we say it is along the Z direction or adjacent to the Z direction. So, 2 1 axis, when we refer to the 2-fold rotation axis, we refer to the direction. When we refer to the glide planes, we refer to the mirror plane or the plane, and therefore, it is 2-dimensional. The mirror planes which we refer to are 2-dimensional planes. On the other hand, the axes are single axis rotations, and therefore, We say that PNA21 is a space group which has a point group symmetry of MM2, an N glide perpendicular to the A axis, an A glide perpendicular to the B axis, and a 2-1 screw along the Z direction or the C direction. In the case of the orthorhombic system, A, B, C and X, Y, Z are one and the same direction because we have alpha, beta, gamma as 90 degrees. So, we can use them interchangeably. Even though technically the correct usage when we refer to the mirror planes as perpendicular to some direction, it has to be X, Y or Z. Now, the X, Y or Z in other crystal systems need not have the 90 degree angle, they can have different angles, but you refer to the X, Y, Z directions. The value of A, B and C will only define your unit cell dimensions. The value of A, B, C will only define unit cell dimensions. So, we can also say in this context that N is perpendicular to A is perpendicular to B, but the correct definition will be N is perpendicular to the X axis, A is perpendicular to the Y axis and so on. So, that is the nomenclature. Now, you see this diagram, the symmetry diagram. The symmetry diagram is showing the presence of the 2-1 axis which is coming towards you, and the presence of the N glide which is perpendicular to the A axis. Now, this is B by definition and vertically A axis, and you see that you have the N glide perpendicular to the A axis. This is the A direction down the picture, and this is the B direction. So, the A glide is perpendicular to the A glide is N glide is perpendicular to the A axis. Let me repeat. So, we have the 2-1 axis associated with the Z direction, agreed, and then we have the A direction which is in this way, and you see that the N glide is perpendicular to the A direction. N glide is indicated by a line and a dot and a line and a dot and so on. So, this is the N glide. Just likewise, we have an A glide, that means A in the direction of A we shift it by 1/4, and that 1/4 shift is in this direction, and you see that we have the A glide which is perpendicular to the B direction, and therefore, all the 3 symmetry elements are described here. So, if you are just given this diagram, in principle you should be able to say it is PNA21 by just examining the positions of the symmetry elements by now, because you have learnt it over the last 1 hour or so in the previous classes, that the way in which we interpret these diagrams. So, you already are an expert to see that the moment this diagram is given, you know the space group is PNA21. And if you get to that understanding of this, then your crystallographic knowledge is reasonably good. And then we also have a situation where this can be interpreted in terms of the equivalent point diagrams. Now, you examine the equivalent point diagrams. The way in which it is generally recommended is that we keep both these diagrams together as we go to higher and higher space groups in order to understand the space group definition clearly, and that is what I will try to do in the next couple of minutes in this particular space group, and that is a generalization of any interpretation of any space group. Here is a diagram which shows you the symmetry dispositions, the positions of where the symmetry elements are and how they are coming and what is the nature of the symmetry element. This is a good example to take it because this is a very straightforward example. It is an orthorhombic system, so A not equal to B not equal to C, alpha, beta, gamma are at 90 degrees with respect to each other. The point group symmetry turns out to be MM2. So, we have a 2 mirror system and a 1 2-fold system, and this therefore is the representation of the A B plane, and this is therefore the direction which is coming out from the board is the Z axis or the Z direction. So, the 2-fold therefore is associated with the Z, the 2-1 screw. Since it is a 2-1 screw, we now mark the screws at this position at 0 0 0, then half the distance will automatically come because of the edges being also carrying the 2-1 screw axis by definition. So, we fill up this 2-1 screw axis first, and then we see that we now look at this diagram and see in this diagram whether we generate these 2-1 screw axis. So, if you like to take this particular point, operate the 2-1 screw axis, you go to that point and you translate it by 1 unit and then 1 more unit you get here, and you see that this 2-1 screw axis is the operation between this point and that point, and therefore, we verify the space group definition with the z axis getting the 2 1 screw axis in this particular projection. Having got that information, then we look at the other two possibilities, which are the n glide and the a glide, and compare that this diagram with those. Now, if this is the n glide operation, then the n glide is going here. That means you should have a translation of half and half. So, which is the point which you will get by symmetry relationship? The point is from here to that one, and that is an n glide operation. And again you see that these two become a 2 1 screw operation. So, you got the n glide operation. Now, you have the presence of the a glide perpendicular to this direction, and you see that the a glide perpendicular to the direction generates this and this point. So, you see that this is the two-fold generated position, this is the n glide generated position, and this is also the two-fold related position because of this definition of the group, and this is also the position of the generation due to the a glide. So, you therefore have 4 equivalent points in PNA21. Now, what are these 4 equivalent points? You can see next slide, but you can write it down. So, some of the assignments may ask you to look at this diagram and write down the equivalent points as we go along, and that is a very straightforward thing, because you take this as x, y, z, you automatically write the rest of the equivalent positions by looking at the disposition of the symmetry elements in the symmetry diagram. So, suppose you are given these two diagrams, you can write the equivalent points. And what are the equivalent points? They appear here. It is x, y, z, and you have the two-fold axis. The two-fold axis is associated with the z direction. So, you get x bar y bar half plus z. So, the second point which you generate from x, y, z is x bar y bar half plus z. Then you have the n glide. The n glide will take you to x plus half. Now comes the question, which is this point number 3 in the diagram here. So, if you look at what is that point number 3 in this diagram, you have several choices. These two are not possible, and what is the choice we have for this one? So, the equivalent point is x plus half, y bar plus half, and z. Okay. So, if this is the a direction, then x plus half. So, if you take this point, x plus half will be what? It will go there. Okay. And then you see that it is y bar plus half. So, you will come here, and so this is the point number 3. Okay. So, you can therefore correlate this with the equivalent points and verify this, the fourth point, where it comes, and if you just go through back and forth between these two slides, in principle you will be able to get it. Now, because of the fact that we have now 3 non-translational components, just like 2 1 2 1 2 1, here we have 3 non-translational components, NA21. NA21 is n involves a half translation, A involves a half translation, 2 1 involves a half translation. So, therefore, there are no special positions in this space group.